Welcome to welcome to the optimization and machine learning seminar series. Today our speaker Volkan Cevher from EPFL in Switzerland. He's an associate professor there, and he's also a faculty fellow of the EC department at Rice University. His research interest span across the machine learning, signal processing, optimization theory, and information theory. And today he's gonna tell us about a very exciting, line of work on training neural networks at any scale.
All right.
Take it away.
Thank you very much. So how is everybody? All right, that's good. I'm a little bit jet lagged currently. It's like, I don't know, actually it's 9 hour difference. So it's 10 o'clock, I think, my body. So it's a little bit weird to see sunlight and so on and so forth. All right, today I've got a very good talk for you. It's a bit of a crescendo, so hopefully everybody's ready. Let's fasten our seat belts. Exits are located there and there. Okay, what we're gonna do is we're gonna talk about a prototypical deep learning problem. And I think I'm preaching to the choir here when I talk about deep learning. But I like this Vapnik's block diagram. There is a generator giving us some data AI. There's this unknown supervisor that gives us labels, numbers, or probabilities given AI. And as the learning machines, our job is to figure out the mapping from AI to BI. If you think about it, this is just a function. You can take, any function class, but the one that is particularly interesting to us is neural networks, meaning that this function will be parameterized by some parameters X, and those parameters will be, let's say, the weights and the biases of the layer. Just to give you a concrete example, consider the single layer MLP. What you see here is that there's an input A, you apply an affine transformation that goes through a nonlinearity, and then you rinse and repeat this linear layer plus bias to make it, deeper and so on and so forth. Now, the supervised deep learning problem with a neural network then is concisely written as follows. You have n data pairs, AIBIs. You want to minimize your prediction given the parameters of the neural network, which will be basically some vectorized form of these weights and the biases, right? And what we will try to do is minimize the loss between what you predict as a function of the parameters, and you minimize that with respect to the parameters as your decision variable. Now, what I'm going to do is I'm going to talk about algorithms that try to solve this at scale, but know that the algorithms that I will describe are much more broadly applicable. You can use them for RL, for supervised fine-tuning, and even things like combinatorial optimization, which will come up in a little bit. If you want to see a longer treatment of these, I actually give a course at EPFL called Training Large Language Models. My material is online, so there's like a longer treatment of some of these topics there. All right. In the beginning, there was stochastic gradient descent. All right, so SGD, Annals of Mathematical Statistics, 1951, is one of the key algorithms that kind of reshaped our deep machine learning. The idea here is that you're given some step size. Let's say here we're simplifying it. Normally, this would be iteration dependent. You grab, let's say, a stochastic gradient, and you update your iterate by just scaling the stochastic gradient, and you do some iterations. All right. Now, what I will do is I'm going to think about this particular algorithm as an instance of a template, and the template will be a minimization template where you are given some dual feedback, something that comes from the dual space like gradients, stochastic gradients, and more, which we will see. And what you're trying to do is somehow minimize a quadratic upper bound, let's say, to your objective. And the idea here is that, let's say you have an objective like this. Typically, you have some linearization of it, right? Let's see. And with the quadratic, you end up, let's say, trying to make progress with respect to your objective with a simplified problem that you can easily solve, right? So what it does is it uses what is known as the Euclidean geometry, which is basically descent in some norms that are endowed with an inner product space, all right? Now here, D is the dual feedback again. Now, let me give you more examples of the dual feedback. So mini batch stochastic gradients are definitely one example. So here, you can use maybe one term from the data or maybe bunch of B terms from the data and get an estimate of the stochastic gradient. But there are also other estimators, such as one that is commonly used or known as the momentum estimator, which is an exponentially moving average of the stochastic gradients, right? But there are other variance-reduced estimators, such as Spider and Storm. Now, it turns out that, this momentum estimator is actually very closely related to Polyak's heavy ball method. Anybody heard of Boris Polyak? One of the key people in optimization, right? So let's say heavy ball method was a way to accelerate optimizations just like as early as 94. But this particular type of estimator is in stochastic optimization can be found in many places. For example, if you're into communications, Prokis was like a key person in communications theory and applications, had a channel estimation work where he uses this momentum estimator to estimate a channel. And then Polyak's book, of course, is like a definitive reference that you should take a look at. To my knowledge, these kind of estimators are also used in neural network training. For example, this Hinton, Rumelhart. A Nestor equivalent version of this that uses an additional memory buffer that has a 2x scale averaging. So you can see other types of estimators as well. Now, in terms of other variance-reduced estimators, there are things like Storm Plus that have optimal rates for some of the problem templates that we're interested, but they tend to require you to do more work or look at more data. And hence, in, let's say, extremely large-scale deep learning, they're kind of no-no because people don't like to, for example, in Spider, compute a full gradient across, let's say, 20 trillion tokens, because that would be crazy to do so. But maybe there are other things that you might be thinking about that might work in this setting. Okay, now why am I talking about SGD? Well, SGD turns out to be a key algorithm because when you're doing minimization with neural networks, the problems that you're interested in tend to be, let's say, non-convex. And you can have traps like saddle points that can, for example, attract algorithms and trap them there. But SGD, if you set things up correctly, you can show that with probability 1, it avoids these traps in non-convex minimization. There's like a history of all these works. Please take a look at my work with Panayotis, who's actually incidentally at NERPS. I've been talking with him this morning for a review. And we know that SGD generalizes. There's a bunch of works on this that look at, let's say, the spectral norms of the weight matrices and talk about the Lipschitz of the neural network and under the training with the SGD. And SGD actually converges, and even for non-convex and with the elephant in the room being non-smooth problems as well. There's a bunch of works, including Dima's work here, right? So chapeau. There's also an understated somehow work by Johansson and Mai that gives some guarantees for non-convex, non-smooth problems to a neighborhood in line with Damek and Dima's results. All right. Now, what I'm gonna do is, SGD is like entry level, right? So what I'm going to do is talk about some of the conceptual improvements for performance gains. And I'm going to talk about these conceptual improvements in the sense that they're kind of algorithmic as opposed to systems level, all right? What I mean, like I'm not going to talk about things like, oh, you can quantize your weights and you can maybe do, you can use your hardware a little bit better, minimize bubbles here and there. This I will not talk. I will focus on two things. One will be on-the-fly adaptation, so methods that kind of adapt their parameters on the fly during training. And then I will talk about things like a priori adaptation somehow, methods that have some sort of a specific geometry for the problem at hand. All right. Any questions? Perfect. All right. So in the beginning, there was SGD, then there was a big bang, right? AKA Adam. So currently, when people talk about on-the-fly adaptation, they basically mean Adam. And anybody who has used, worked, or studied Adam goes through the following stages. The first stage is, you go use Adam. It just works, right? Like it's a proven formula. But if you're in the industrial setting and you're running it for, let's say, a very large model, your manager will go and say to you that you must tune the parameters because, you need to get that squeeze 2% here and there. That makes whatever millions of dollars of improvement. So you must do this. Then on the academic side, people go, hey, Adam works. We must prove why it works, and we must, show the optimality in whatever L0, L1 setting, and so on and so forth, right? And then lately, you will see that people start talking about algorithms with some sort of a geometric adaptation that will beat Adam, and this will be today no exception. All right. But when I talk about, on-the-fly adaptation, I just want to, completely disambiguate what I mean. All right. So let's say you're trying to do optimization and, let's say we are doing gradient descent. What can we tune? Well, the thing that we can tune is, let's say, the step size, right? And the most basic, theory on this is the following. Let's say you have a Lipschitz continuous gradient objective function, right? So by Lipschitz continuous gradient, I mean this. You query the gradients at two locations, look at the differences, and you just upper bound that by a constant L times the difference of the query points, right? You can use norm, dual norm here and there. But the point about this is that when you have this Lipschitz continuous gradient, the L constant is globally valid, right? And that tends to be really conservative. So let's say you have an objective like this. Here, things are smooth, but here, things are a little bit curving fast. You need to be able to still, adapt or work with that setting. Your constant will be, for example, needs to be valid here. And what this gives is a quadratic upper bound. And by minimizing this quadratic upper bound iteratively, you get gradient descent. And the step size turns out to be 1 over the Lipschitz constant that you can use. In fact, you can do maybe 2 over L. And there's more story there. For example, Yushan actually had a tutorial talking about larger unstable training regimes, right? But typically 1 over L is the worst case optimal. If you just look at Yuri's book, he gives an example where you can show that, there is a function that resists if you use any other one that will 1 over L turns out to be optimal, for example. Okay, good. Now, the step size choices, when you have stochastic gradients or even deterministic gradients, the other approach is smooth until guilty approach. I call this the smug approach, right? Here, the idea is that, you actually say, hey, I'm a, optimistic person. I'm going to pick a larger step size. Yeah. Until certain things happen, I'm just going to roll with it, right? So, I mean, this kind of a thing kind of works here. You can start with something large and somehow progressively, monotonically decrease your step size. And the advantage being is that, you can actually gain quite a bit. If your objective was smooth to begin with, you can actually approach a solution faster and you win, right? Yay. Then there are, of course, other approaches that generalizes this. So there is the coordinate-wise smug approach. So here you basically think that each coordinate has a different step size, and you try to adapt your step size coordinate-wise, right? This is kind of nice because, the parameters that proportional to your decision variable size, right? Then there is the hella smug approach. Here, what you try to do is basically, try to adapt to the fullest extent with a linear preconditioner to the geometry at hand. So if you have a quadratic, maybe using the Hessian there will give you, let's say, even a one-step convergence, all right? So I hope these things are clear. Good. Now, here's the Adam algorithm. What I'm going to do is I'm going to ignore this debiasing stuff with an appropriate initialization here and there. What Adam algorithm is actually very simple. So for your dual feedback, you use the momentum estimator. All right. So for the smugness, you use this coordinate-wise smugness approach. So you define a variable metric by coordinate-wise integrating the energy of the gradients that you've seen so far. And you can use different averaging constants, beta 1, exponential moving averages, beta 1, beta 2. And then, sorry, and then you can view in a similar way what SGD was doing. So your dual feedback is the momentum, and your, let's say, quadratic upper bound coordinate-wise stretches these quadratics, all right? Whereas the let's say the preconditioning, the linear preconditioning that you get is defined by this V update, okay? But then the question is, how do I get the V update? Well, it turns out that, there's a whole history coming from online convex optimization. There is the McMahon-Streeter paper from 2010 called that actually did this the first. All right. They even did the coordinate-wise version. Then John Ducci, Elad, and Yoram basically generalized this with the proximal update. So there was the composite minimization case, and they did the hella smug version. Francesco Orbona actually has a pretty good lecture notes on this that are also on archive. So if you're interested in online optimization, Francesco also retains like a nice blog on this. And then we're kind of guilty in giving, guarantees for these kind of algorithms in ICML 2020, right? But in practice, there are also some enhancements, let's say, for Adam. And if you go over this, for example, you will see that Adam will use a weight decay parameter and the step size scheduler, all right? And typically what happens is that your step size parameter is a constant. Sorry, gamma. Your weight decay parameter is a constant, and there is this additional dimension of a step size scheduler. Anybody heard of a step size scheduler here? I'm guessing yes, yeah. So what that is, actually the weight decay originally is the decoupled weight decay enhanced in Pratt and NURBS 1988. I don't know how many of you were born by that time. Yeah, papers that existed before you were born do not count, right? That's the idea. So what the step size scheduler does is very simple, right? So there's the constant stable weight decay, approach. Here, if you recall, what we're doing is we're building a variable metric. And if you're building a variable metric, initially you have stochastic estimates, and you don't want to kind of commit to those stochastic estimates because you can have variations that can kind of, move you around. So you end up warming up until you build some sort of a, let's say, good variable metric. Then you let the algorithm in the constant phase kind of run, right? So you don't do anything to the algorithm. And then there's this ramp down phase. So some people use linear ramp down, some people use whatever square root ramp down and whatever. The point about this is that, remember, we're doing non-convex optimization, and in the end, we're also doing stochastic optimization, and we need to provide an output. Yeah. If we were convex, we could just average things, but in non-convex optimization, averaging is a terrible idea. What else can we do? Well, it turns out that by linearly ramping down or quickly ramping down, you can actually give last iterate guarantees for your algorithm. And in fact, again, in another understated paper, François Glener's work, for example, shows that for non-convex minimization, the linear ramp down, you can shave off the logarithmic factors in the numerator and get the optimal worst case rate by literally linearly changing your step size. And there's like neat theory about this. But people also use, bunch of heuristics, cosine scheduler here and there. They're all good, right? As long as it works, it's okay. Very good. So my own research kind of went through the stages in the sense that, Adam was popular. We were trying to get algorithms like Accelergrad that are kind of universal and adaptive. What I mean by that is that, like adaptation kind of refers to the fact that oftentimes the problem parameters like the Lipschitz constant is not known. And you try to come up with an algorithm that kind of adapts to this parameter, gives you a step size, gives you convergence without knowing the problem parameters. And Accelergrad was unique in the sense that it was a method that did not care if you were giving it stochastic gradients or subgradients, and it didn't actually need to know if the objective was non-smooth, smooth, or it's non-smooth or smooth, right? It would converge optimally in all cases, right? You didn't need to tell the algorithm that you were giving stochastic gradients or the full gradients. If the objective was Lipschitz gradient, this would give you 1 over k squared rate. And Unix grad is a little bit enhanced version of that. Then we gave, for example, guarantees for Adam with the coordinate-wise adaptation. I think this was the first one. And then we looked into other variance-reduced estimators, Storm Plus, for example. And, it's a very acronym-driven research theme in machine learning. So we developed the undergrad method. Do people know graduate student descent? It's kind of similar. Here, our idea was to use the undergrad to reduce the dimension dependence on things. When you work with undergrads, things are cheaper, for example. So that's the idea. We also developed algorithms, second order methods, extra Newton. So it's Newton, but extra. That gave 1 over k cube guarantees. It's a little bit worse than the Slater's lower bound of k to the 3.5. But, in practice, this gets to 3.5 rate. We didn't care too much in the end because I think it was just an artifact of the proof technique that we had. But, we looked into, so this algorithm would also adapt to stochasticity of the oracles and so on and so forth. And we had this universal stochastic convex optimization approach with Anton, where we use different kinds of estimators in adaptation. It was fun things. All right, it turns out that, I actually did mention this other grad kind of things that you use the competitive ratio to get to those VK updates, right? So what other grad is actually this, let's say, online optimization based algorithm than Adam. It turns out that Adam is basically a diagonal version of the other grad method with the momentum estimator, right? And as opposed to just adding up, let's say, accumulating the gradients in a monotonic fashion, you use the exponential moving average. All right. So what I'm going to do is I'm going to tell you the hella smug approach here. So as opposed to looking at the gradients coordinate-wise, so John's paper, you take the gradient outer products, kind of like the Fisher approximation to a Hessian. You accumulate this. Okay, so there's a typo here. So you get your stochastic gradient, you develop your variable metric, you run with it, right? The same approach. Okay, but if you think about it, Adagrad did not take off in the way Adam did. The reason being is that if you try to implement this algorithm, the storage and the efficiency becomes a very difficult problem. Why, you ask? Great question. Let's just take a simple example, single layer neural network. We're friends here, so I'm going to ignore the biases. Right? So you have a weight matrices and 2 weight matrices here. Let's say they're m by n and n by m. All right, so let's take them, vectorize them nicely. All right, and now let's take a look at the dimensions of the variable metric, which is 2nm by 2nm, and the gradient is 2nm by 1, right? So h here is not the variable metric, but huge variable. The gradient is a great variable. And if you wanted to store this, just like impossible, right? So for a million dimension by million dimension, you end up looking at trillion dimensional variables. Just, it's not going to fly. But there was a key idea. And here, as opposed to looking at these fully dense Hessian approximations, you can think about maybe structured Kronecker factor approximations. All right. Here, with this, actually, you gain quite a bit in the sense that you can say, hey, let's say my variable metric H is a Kronecker product of a right preconditioner times a left preconditioner. All right. In this particular case, right and left here, these are matrices, right? And you choose them appropriately in the dimensions of the layers themselves. Then you use a simple linear algebra identity, which says, hey, H inverse G in this particular case is a vectorized form of L minus 1/2 G, where G is now treated as in the ambient dimension of the matrix itself, then the right minus 1/2. So you see the left preconditioning and the right preconditioning on the linear preconditioning on the gradients here. So here the weights of the neural networks are treated explicitly as weights. And there's a bunch of history, like some of these left and right factors are picked according to like Bayesian stories and so on and so forth. I think Regis Gross's lecture notes are quite interesting. I recommend that you take a look to learn more about the history of this. But you see, first order structured preconditioners result in efficient algorithms. So when I first talk about the Hella-Smug approach, this is the Adagrad fool, John's baby, let's say. Here, the preconditioner is the summation of the outer products, right? So you have the standard update rule. Then Noam Shazir had this ada factor. Here, you look at left and right preconditioning, and you choose your left and right preconditioning in such a way that you precondition the rows of the weight matrix and the columns of the weight matrix, and the degrees of freedom is just like, oh, delicious, right? As the neural network grows, this has like a vanishing fraction of numbers to precondition the neural network. Very good. Then came the shampoo approach. So you use a left and right preconditioning. I will actually tell you what this thing is in a little bit. Then there is the soap approach. You know, the shampoo is named shampoo because it comes before preconditioning the washing the hair, right? Conditioning the hair. So soap is before the shampoo or whatever. I don't. So there is a shower theme here. So you make up your own mind depending on how you do your showering. But you know, you can do one-sided version, left and right, and you can give some guarantees in terms of convergence. So I like this one as well. All right. You can also do second order approaches here. So first of all, none of these things are second order, right? Because they're just based on gradient information. But what you can do is actually you realize that when you're computing some of these gradients with neural networks, you can economize on certain computations to get Hessian estimates, actual diagonal of the Hessian. Actually, the earliest one is the one that I know from Mike Mahoney, which is pretty much understated, but there's the Sophia approach, which was quite popular that came after, pretty much the same thing, if you ask me, conceptually speaking. But these things require even more hyperparameters, and you need to ask yourself how many hyperparameters I'm willing to tune. But you know, there are some approaches that actually do second order, use explicit second order information. All right, so far so good. Very good. Now, you see, Adam, which is the king of all algorithms because of the number of citations that it has and accumulates over the time, you see, machine learning at the time was, you know, a niche topic. So you know, small conferences like ICLR tend to be co-located with other conferences, big conferences like AI Stats, you know. And AI Stats was in San Diego. So I thought, hey, you know, we just send this stochastic spectral descent work that we have and presented it AI Stats, which was same hotel, and I think you were there, right? So we presented the following work. So one thing that I was interested in, because I also read papers from Soda, stock, these kind of things are also interesting. So there was this Yin Tatley and Sitford paper at Soda that won the best paper award. The idea there is to get a complexity improvement on multi-commodity flow problems by using the non-Euclidean geometry. So the idea is very simple. So if you remember, SGD followed this particular template with the 2 norm here, right? And what they did there is to not use 2 norm, but use the L infinity norm, all right? So in that case, the update you have is actually a non-linearly preconditioned version of the dual feedback, all right? And I use the sharp operator here. Why? Because Yuri uses it in his huge scale paper, and Yuri is the first one to use it. So I think he uses the musical notes for the mapping between spaces and so on and so forth, sharp operator, natural operators, and so on and so forth. So what it does is it takes the dual feedback and changes it in a nonlinear fashion, all right? And to explain, it's not that difficult to solve this problem. I do that in my first handout in my math of data course, right? So this is like a nice homework exercise or a classroom exercise. But I want to make this a little bit simplified because I think it will make a big impact. So this particular nonlinear precondition, you can write it as the linear minimization oracle of the dual feedback times the dual norm of the chosen norm here. All right. So what is a linear minimization oracle? Well, it's one of the arguments of the dualization problem here, right? So people know about dual norms. So you can compute the dual norm of a given norm, right? And here, the linear minimization oracle is that you take this linear objective, and it has a big role in this Frank-Wolf method that will appear in a little bit. And the first time this linear minimization oracle is used was in my friend Martin's paper. So, chapeau to Martin. So let's just put him there. You see, it has two components. One is the dual norm scaling, and it actually comes for free if you're solving this problem, because literally the objective value of this problem is that dude. And you just need to solve this optimization problem. All right. So far, so good. Pretty good. So in the AI stats paper, so I gave two examples because I was inspired by the L-infinity norm. I said, hey, let's use the L-infinity norm for the weight biases, right? These are vectors. And the matrix equivalent, I wanted to treat the weight matrices as weight matrices because nobody was treating them as matrices at the time. And I wanted to use the Shetton infinity norm or the spectral norm. All right. And in this particular case, if you use the L-infinity norm, your update is actually quite simple. So you can take a look at this. You see that the dualization basically gives you the sign of the dual feedback. You scale it by the one norm of. And for the spectral norm, you take the matrix sign or the polar of the matrix scaled by the nuclear norm of the dual feedback, right? And, so it's the matrix sign when the dual feedback is square, polar when it is the rectangular. The reason why you call it polar is very simple. If you apply the singular value decomposition, right, you can think of the U and the V matrices as the, let's say, the polar angle, right, and the singular values as the radii, and you throw away the radii, and you have your polar factors, so to say, right? So the matrix sign basically just takes this product of UV, and it turns out that, you can compute this pretty easily using either randomized linear algebra or a quadratically convergent Newton-Schulz method, typo here, or a QR dynamically weighted Helly algorithm, which is a cubically convergent and communication optimal QR-based decomposition method. All right. Now, the old people here are thinking, hey, SVD, these kind of expensive. It turns out that none of these operations, when it comes to neural network training, is expensive. In fact, if you consider very large neural network training, they have a relatively vanishing overhead. Just to give you an idea, I mean, if your dual feedback is low rank, you can't beat the randomized linear algebra. This is what I gave here because we were directly using stochastic gradients and they were very low rank. And you could use randomized linear algebra very efficiently to get R times, M times N complexity to get to these matrix sign. Newton-Schulz uses matrix multiplications, and you use, I don't know, 5 to 10 iterations. Currently, there is the Polar Express version that has a locally cubic convergence guarantee, but does still 5 iterations, I think. But the point about this is that, you look at the backpropagation cost for computing the gradients, right? It has L times S times M times N times B. That's a bit of a mouthful. So for a microbatch size of B, sequence length of S, and the number of layers L. And if you look at the complexity of this, the relative overhead is basically T times N divided by BSL. Assuming sufficient number of GPUs, i.e. the model is large, this just vanishes, right? In fact, you can take a look at it for, I don't know, 20, 30B models. This is less than 2% overhead. All right. Good. It turns out that this algorithm is very closely related to Lars, Sin SGD, Signum, Lamb, Lion, Muon, Shampoo, Lion, K. That came after. All right. Now, in the convex case, my PhD student and I, we developed the accelerated version for just convex minimization. And at the NERSC 2015, we had the preconditioned version. Here, just like you do online adaptation, you can also use online adaptation in the non-Euclidean descent. And the updates are a little bit more complicated, but you can do it. And some of these are also reinvented now. All right, but let's talk about linear minimization oracles, because the story did not end there, because I want to build up towards a very dramatic moment that is coming up. All right, so here's the definition of the linear minimization oracle. All right, so you're given D, what you're trying to do is, you're minimizing with respect to some constraint ball. All right, so when this constraint ball is the L2 norm, what you end up getting from the LMO is very simple. You take the dual feedback, you normalize it with its L2 norm, you negate it, and that's your output. All right. And this has many useful properties. I mean, if you look at the norm of the output in the chosen norm, it has to be the constraint, right? Or zero, right? Depending on whether the dual feedback is greater than zero, the norm of the dual feedback is greater than zero. There is this homogeneity property that if the constraint is scaled, right? I'm not using gauge functions here. Things need to be symmetric. You scale the output of the LMO. And you can do a bunch of things. For example, layer-wise, you can basically define some norms and then take the maximum over all these norms over the layers. And then you have a nice decomposition property of the LMOs across layers. All right. Very good. So in the case of the gradient here, like if you were to do L infinity, you get literally the sign of the gradient, right? Negated here. If you do to L1, you get, let's say, one of the coordinates, for example, the largest coordinate, and so on and so forth. Yeah. As you can see, it kind of stretches things depending on the geometry that you put. All right. But you see, this LMO, for example, for the L2 norm was, kind of scaling the dual feedback to have unit norm, right? But these kind of things are already used in machine learning. Anybody heard of the normalized SGD? Practitioners love this or used to love this. For example, here's the simple version. You use your momentum estimator for the dual feedback. You normalize, continue, right? Practitioners love this because it, mitigates exploding and vanishing gradients. Anybody did here any real training, like skip connections and the gradients, you have pre-norm, post-norm. If you put these things together, you start backpropagating to even the epsilon value you put in the denominator of the atom will matter. You know this, right? So things like this kind of normalizes the gradients and gives better signal to each layer and whatever, right? So these kind of things are used and people love these kind of things. But the theoreticians also love this because, you can argue that, it has rigorous convergence guarantees. I think this Kroshow paper is the one to take a look. There is avoidance results, there are robustness guarantees. You can talk about adaptation to Hölder smoothness, L0, L1 smoothness, right? Just the throw of theoretical knowledge here and there. Yeah. Now, just thinking about this out loud, you say, hey, conceptually, this is very similar to a normalized steepest descent. Yeah. So I can see there's some excitement in the front row, right? So here, the idea is this, right? So let's say we're trying to do minimization. Let's put around where we are a trust region, let's say an L2 ball around our current iterate. All right, let's say your step size is small enough that you put a linear model of your objective function. All right. And if you look at this, the output you get is actually that, right? Provided that your dual feedback is the deterministic gradient. You can see this in the chapter 9 of Boyd and Vandenberg as early as 2009. Yeah. And conceptually, you can also generalize this to the non-Euclidean geometry, right? So you can say, hey, I'm going to put Schatten infinity norm there, and I'm going to use as opposed to the gradient, I'm just going to use my dual feedback, whatever stochasticity. It turns out that just switching the gradient, deterministic gradient, with stochastic estimates, there's a phase transition in analysis, in the difficulty of analysis, right? So it's not a trivial change, but you see that the algorithm you get is basically this one. So xk plus step size LMO of the dual feedback. There's something missing from what we discussed so far, right? In the sense that the dual norm scaling is missing. Do you see it? Right? So what I described before had the dual norm of the dual feedback here, but this one doesn't. It turns out that this algorithm is known as the stochastic continuous greedy method. Anybody know about submodular optimization? Do people know Jan Mondrak, the husband of the late Maryam Mirzakhani? Right? So he had this algorithm in stock 2008 to solve combinatorial optimization problem that had the submodularity structure. And then Amin Karbasi, Aryan Mokhtari, Hamed Hassani had the convex version of the stochastic feedback momentum estimator in their NURBS 2019 paper. All right. You see, instances of the stochastic continuous greedy is in fact the algorithms that we know and cherish. Things like normalized SGD is stochastic continuous greedy method with the L2 norm. Lars Lamb, you change the L2 norm, the momentum estimator, you obtain these algorithms. With L infinity norm, you get RP prop sine SGD signum Lion type of method. And if you use the S infinity norm, you get an algorithm known as muon. More on this later. But as a bonus, you can actually change the linear model with a quadratic model as well. It turns out, you can put your quadratic model there and you get a clipped version of the algorithm that has a better behavior locally, right? Because we know that SGD doesn't converge with the constant step size unless you have things like strong growth condition, which is a necessary and sufficient condition for SGD to converge with constant step size, right? You would have this if you have, let's say, overparameterization, but in general, we don't have overparameterization. And there's an oral at this NURBS tomorrow morning. If you're interested, come to NURBS. All right, so instances of the continuous greedy template. So normalized SGD is one, sine SGD is another one, signum and muon. So let's talk about this. Normalized SGD is something like the stochastic subgradient method, right? If you talk to Arkady, anybody know Arkady Nemirovsky, right? The gentle giant. He always told me that, we wouldn't be interested in the size of the stochastic subgradient. You only care about the direction. So it's always normal to normalize that, right? If you look at Boris Polyak's paper, he also normalizes all these things. Good. So with stochastic gradients as dual feedback, you can see it in one of my collaborator, Kfir Levy, and his advisor, Elad and Shaleh Schwartz paper. With the momentum-based dual feedback, to my knowledge, it was first characterized by Ashut Chutkowski. Now, sine SGD and signum analysis, so sine SGD and signum was also algorithms by Jeremy Bernstein et al. They require increasing batch size for convergence. There was Martin Yagi's paper with Praneep that used error feedback to fix this issue, right? They actually give an example from Boris Polyak's book as a counterexample that if you use constant step size, you cannot converge with sine SGD. So the examples are pretty old. The first convergence with sine SGD type of algorithms that I know is Michael Kroshow's paper with Francesco Robana in NURBS 22. Now, muon algorithm, which is momentum orthonormalization with Newton-Schulz, they use the momentum estimator, and for the LMO, they use the spectral norm. To compute this LMO, they use the Newton-Schulz algorithm. So if you're using QR decomposition, maybe you should call this MUOC. If you're using polar express, you should call this MUOP algorithm, right? It didn't have any theory, and they just suggested to use this for the hidden layers. All right, so far so good. Very good. Now, I'm going to pause for dramatic impact here because what I called Frank Wolf. Anybody heard of this algorithm? It's the usual suspects. All right. So what is Frank Wolf? So Frank Wolf is an algorithm that was developed because linear programming was so powerful that they were trying to figure out how can we apply linear programming as a subsolver for, let's say, non-linear objective functions, right? And there the algorithm is simple. You have an objective, but you have explicit constraints. So right now, what I will be talking about is deep learning with constraints. The algorithm is simple. You take the LMO of the dual feedback, you take a simplicial combination with your previous iterate that you assume that already is in the constraint set. And the constraint set is convex. By taking this simplicial combination, you guarantee that you always satisfy the constraints. And as opposed to performing projections onto the sets, you compute the LMOs. And there are many problems where computing the projection is much more expensive than computing the linear minimization oracle. If you worked on sparsity, you know, for example, whatever the group norms, LMOs are tractable, projection onto some of these group norms are intractable. All right? Good. So for a review on Frank Wolf, Clarkson paper is a good one that people often miss. Martin's review is also pretty good. He named the LMO there, right? And then there's a recent one that I also recommend, which is pretty good, nicely written. So for this method, for convex minimization with momentum-based dual feedback, was first done in Arjan's paper. Now, what I've done with my collaborator Suvrit and my PhD student Alp, who's got a thesis distinction on this, we did variance-reduced feedback for non-convex problems. So things like spider, conditional gradient sliding. And it turns out that nobody cared to do the non-convex minimization with the momentum-based dual feedback, which was our ICML spotlight, right? Now, for those of you who work on this, so we established so far that this is like the normalized SGD algorithm. So the momentum estimator is good, right? There's this term that kind of looks like weight decay, no? Yes? Say yes? Yeah? Yes, okay. Yeah, the tacit silence is, so silence here is a tacit yes, yes. All right, so, well, look, there was this decoupled weight decay paper. By the way, don't worry, the slides will go very fast because the rest of the stuff is like plots. So if you're worried about the time, don't worry, we'll make it. We'll make it. So, there was this decoupled weight decay paper that argued that, hey, don't treat the weight decay as a Tikhonov regularization, right? No matter what you have here with Adam, with the preconditioning, always have this kind of a weight decay factor, right? And in problems, the weight decay works better. We know that Adam with weight decay generalizes better, right? If you think about this, the correct way to think about weight decay actually is not this decoupled weight decay thing that is proposed by Frank Hutter's paper. Take a look at this. Here, let's say we're performing Frank Wolf with dual feedback with a radii gamma divided by lambda. By homogeneity, you can take it here, and you have the normalized SGD with weight decay. But in the light step size, and what you scale your gradient with is the constraint radii for that layer. So what I argue is that the correct interpretation of weight decay is actually no longer the weight decay. That's literally the Frankfurt step size. And we are trying to solve constraint problems when we are putting weight decays in here and there. All right, so here's a taxonomy of algorithms. SGD, you can think of SGD as the dual feedback as the stochastic gradient, and your preconditioner is just identity. Momentum estimator, you put your momentum estimator, your linear preconditioner is the identity. Adagrad, what it does is it builds a coordinate-wise preconditioner by accumulating the gradient energy per coordinate. You use the stochastic gradient. RMS prop, you use the stochastic gradient. You use the Adagrad type of preconditioning with the exponential moving average. Then came my paper with the stochastic L-infinity descent, which was in the stochastic spectral descent paper. You use the stochastic gradient and your linear preconditioner depends directly on the gradient energy, on the coordinate. So the updates are actually nonlinear. Stochastic spectral descent, you can think of it as a right preconditioning, left preconditioning, right and left preconditioning, with your right and left preconditioning as the gradient outer products. Then came sine SGD, same as stochastic L-infinity descent. You use either the stochastic gradient or the momentum estimator. Shampoo uses the stochastic gradient, does the same type of idea as RMS prop and Adam does in terms of averaging. Unconstrained version, or muon, uses the momentum estimator and uses the same type of nonlinear preconditioning, left, right, left, and right. All of them are equal here. Okay, so how do we choose the constraints for each layer? Well, it turns out that modeling the optimization problem as a black box is the wrong way to go. You are defining the problem. It's like, looking at optimization problems, thinking about game theory, and then forgetting the fact that you are both players, you are deciding everything. Forget about black box optimization. When we're training neural networks, we are allowed to choose our constraints because we are running it. So for this, okay, I think given the time, I'll go a little bit quick here. You can use things like tensor programming and argue that you want the bounded features to result in bounded features across the neural network so that your neural network is Lipschitz. For this, you can use the spectral norm to control the 2-to-2 operator norm where the features propagate along the neural network. For the input and output layers, you need to be a little bit more careful just because things like mu-p theory, maximal update parameterization that vary about, let's say, putting a lower bound on the updates and an upper bound so that your training is stable with the parameterization that you have, it turns out that the input and the output layers are kind of abnormalities. Reason being is that in mu-p, you make the width of the layers go to infinity, and yet in neural networks, your vocabulary size is so large that your widths are not going larger than the vocabulary size. And those need to be treated a little bit more specially. And I have some theoretical results in my earlier works that show 2016 that if you want to adapt to the softmax loss in the output layer, you better use sign-based updates. L-infinity norm adapts best. You get theoretical advantages. All right. So for this, for image domains, we recommend spectral, and sign for the input, output layers. For one hot input, sign, spectral, and sign. All right. All right. So here is the algorithm. So pre-game actions, you initialize. So there is a whole theory for this that I'm happy to talk in the afternoon if those of you are interested. You choose the scaling of the intermediary layers, step size, input and output layer scaling. So there's a ton of theory that goes through here. You get your momentum estimator. You do your layer-wise LMO. And the algorithm is simple. You have the Frank-Wolf step size and the radii for each layer. Here's the algorithm. And then when you do that, this inversion becomes extremely clear. So if you look at things like muon that uses matrix sign Adam in the input and output layer, you have the decoupled weight decay, right? Look at this. You don't have weight decay in Frank-Wolf. You have a step size. You have the radii. When you do this, you have transfer of the step size and the radii for neural networks that kind of scale. So this is very nice for hyperparameter transfer. All right. And then we use this for speed running. So by the way, speed running is kitchen sink descent on training an LLM. This is not just about the algorithm. It's about everything you do with the architecture, the QK norm, and the let's say whatever the quantization tricks that you do, right? So algorithm is nothing but an aspect of speed running. All right. And changing everything is what matters in speedrunning. Everything. I mean everything. All right. And we did really well there. All right. So here's some theory, and you need to be careful with the theory in terms of what you do. The point is that this was the scaling Jordan Keller was suggesting in the muon paper. It looks like you can have transfer, but then all of a sudden things can shift. So if you do the theory right, you can actually have nice hyperparameter transfer across scales, all right? So we do good, yada, yada, yada. The point about Frank-Wolf is that you're not surprised that, your constraints are satisfied. If you use weight decay and plug things here and there, you don't know what's happening. They're just growing, all right? So here we did a study also on the batch size. We have the best batch size dependence, and there's some interesting theoretical results that we're working on because it seems like the optimal step size transfers across batch sizes. All right. Now, last example that I will give is that, we talk about LLMs, but anybody work with ImageNet? Data efficient transformers? Some of you did, right? Do you know how painful it is to train the base model? Takes like a week. But maybe you guys reach here and you have some I don't know, H200s or whatever, B200s now that they take a couple of days, but still a problem. And there exists a highly tuned baseline, Google's baseline, right? What we did is actually beat that baseline by a lot. And what was cool is that you can train and tune the tiny model, transfer to the base model, and get 30% less epochs, 40% wall clock time, and 80% less iterations. And that this weight decay perspective turns out to be very important. And of course, the clipping version that I mentioned, which is an oral tomorrow, also makes a difference. All right, let's end the talk here. So what I would like to say is that there is a tension between machine learning and optimization. In optimization, you're given an objective and you're saying, okay, my only goal is to minimize the perplexity. But machine learning doesn't care about that. It's for generalization. In optimization, we care about, algorithms that obtain the best rates for the worst case, right? In machine learning, you don't care if that algorithm works for any other problem as long as it gives you the best performance for the biggest run that you're going to do. And this creates a major discrepancy between what people do in theory and what people do in practice. And oftentimes, the part that I completely ignore, the system level stuff, can make or break an algorithm. It doesn't matter if your algorithm is optimal, as long as you don't have the matrix multiplication Triton kernel, you don't care, right? But it turns out that I think that the promising thing is to think about neural network training is with constraints. And I think this Frank-Wolf perspective has quite a bit to say. And in addition, there are other twists that you can put into the problem, like changing the data mixture, the order of the data that you feed. For example, you can use all spectral for the layers. You change your data mixture, and all of a sudden you get a 50% speed up. And then you say, hey, you know, use a little bit of the theory, you change your input and output layers. The theory says you get a major speed up. You can put in addition data mixture and you get additional speed ups, right? So what I would like to say is that the theory has still a little bit to say, and that you need to think a little bit holistically, that the algorithm and the architecture and the systems, they need to work together when the problems are so expensive. Thank you for your attention.